but she just mentioned that she's in the final phase of her PhD work, so we get to hear the meat of the work that she's been involved in over the past 3, 4, 5 years, whatever it is. So I think I'll turn the floor over to Sylvia and help me in welcoming her. So, welcome.
My advisor is actually from Vancouver, and our lab has a big Canadian flag on the front, so that's the very first thing you see. She has a lot of pride in this. Thank you for welcoming me. My name is Sylvia, and I'm presenting safe and efficient control for dynamic systems. And the motivation is pretty straightforward. We want our autonomous systems, our robots, to be able to operate efficiently in real time in scenarios as particularly where you need to make real-time decisions, such as among humans. But you also want to maintain safety. And there are a lot of safety-critical scenarios that currently autonomous systems are not very capable at handling. And so how can we balance the need for safety and efficiency at once? Unfortunately, this is often two sides of a spectrum, where on one side you can have something like reachability analysis, which is my background, which is essentially dynamic programming, where you very, very carefully can compute the optimal trajectory for your system to take to get to its goal while avoiding obstacles along the way. And this can be robust to disturbances, it can handle obstacles, it can handle moving obstacles, but it's extremely slow to compute. On the other side, you could have something like rapidly exploring random trees, where you just abstract away your entire system to a point in configuration space, pick some waypoints, connect the dots, and generate your goal there. Now this is very nice because it's very efficient to do quickly, but it may not capture disturbances or the dynamic behavior of your actual system. So when you try to follow this path, you may find that you can't follow it exactly, and it can lead to collisions. So how do we balance the two? So this is my outline, is trying to tackle this. So first I'm going to start on the safety side and introduce reachability analysis. And then we'll try to incorporate in efficiency through a project called Fast Track, or Fast and Safe Tracking. And then if we have time, I'll get into some of the other directions that we're going in for this. Okay, so let's start with safety. How do we ensure safety in an autonomous system? Well, we do it in my lab through something called HamiltonJacobi reachability analysis. And in fact, the code base that I use and a lot of these animations that you see are entirely from Ian Mitchell's level set toolbox code base, so I highly recommend that if you haven't used it already. But in a reachability problem, I have a dynamic system where its state is dependent on the current state, its control, its input, and the disturbance to the system. You can typically think of this as like wind acting against you. And you also have a goal that you're trying to reach, so a goal in the state space. And you want to find the set of states that you can start in such that you are guaranteed to be able to reach the goal within your time horizon. And with that, you want the controller that allows you to get to your goal. This can also be, let's say, an obstacle, and you want to find the set of states such that if you enter that set, you may end up running into the obstacle if the wind is acting in the worst case. But let's first start with the goal situation. So to solve a reachability analysis project, you first lift this to a higher dimension, and you define a cost function over this. So in this particular case, my cost function is an implicit surface function that is essentially saying if I'm inside of my goal, the cost is negative, which is good. If you're outside the goal, the cost is positive, bad. And usually you do this as a sign distance function, so the closer you are to the goal, the better. Now next we want to build up a value function that will tell me, starting from a particular state, will I be able to reach the goal? And it's a little bit complicated, but we'll build it up one step at a time. So first, this is my trajectory notation that I'm going to be using. This says if I start at a particular state and a particular time, and I apply my control and my disturbance until time t, this outputs the state that I end up at. And I want to look at trajectories of my system and measure the cost of these trajectories, because I want to measure how close they get to the goal. So I ideally want to find trajectories that get negative cost, meaning that they end up inside of the goal. So since I want to measure the cost of these trajectories, I'm going to put my cost function here, measure the cost of these. And now I'm interested in the cost of these trajectories in particular when they are the most negative. So I want to find out the closest that they ever get to the goal over time. So I have a trajectory over time, and I want to find out the most negative that its cost gets over that time horizon. So I'm going to add in a minimization term here. So any cost that this comes out that's a negative, that means that the trajectory was able to enter the goal. Now one more step. I am not just interested in any trajectories of this system. In particular, I'm interested in the optimal trajectories. I want to know if I am doing my best to try to reach this goal, and the disturbance, in the worst case, the wind, is being as difficult as possible, and is always working against me. Will I be able to reach the goal regardless? So I have my soup imp over this, where the disturbance is going to try to maximize this cost, and the control is going to try to minimize this cost. Now, this is a very complicated thing to try to solve for, and so instead we solve for the Hamilton-Jacobi partial differential equation. So this is our update equation, where I discretize this entire state space, and I solve this partial differential equation at every single point in that state, at every single point in time. This is essentially doing dynamic programming to end up solving for this value function. And this equation looks like this. So at a particular point in the state space, if I'm considering how the value changes with time, it is according to this Hamiltonian, which for those who haven't seen Hamiltonians, the Hamiltonian takes into consideration the min over u and the max over d from up here. So this is essentially trying to do gradient descent. I'm looking at the slopes of my cost function, and I'm trying to drive my system down to more negative values. But I'm constrained by my system dynamics. And the disturbance is trying to do the opposite. So that takes care of our min and max. We also have the min over time that we have to throw in. So there's one more step that accounts for the minimization over time. Okay, that was a lot of math, but what it actually looks like when we implement this is something like this. So here I'm growing my value function over time, and you see the time horizon that I'm interested in happening up here. In this particular case, I'm looking at a time horizon of 15 seconds. When I reach 15 seconds, I'm now interested in this value function where the value is less than 0. Because where the value is less than 0, that corresponds to a trajectory that manages to attain a less than 0 cost over time. And so I slice this value function at 0, flip it around, and now this is my reachable set. This is the set of states for which if I start inside of this set, I am guaranteed to reach my goal within the time horizon despite worst case disturbances. So this is really nice. We can also add in things like obstacles. So here, let's say I have some obstacle that I know of. In this case, let's imagine it's static. Now I define a second cost function over this that's positive inside and negative outside. So high cost inside of the obstacle, low cost outside of the obstacle. And now I have to have my function wrap around this cost function because I want to make sure that it never enters inside of this obstacle. To do that, I have to throw in a couple maximization terms, as you see here. But what it ends up looking like is one of my favorite videos that I've done, is because it's just so beautiful to see this in action. So you see that it kind of like wraps around this obstacle function like molasses or something. And then once I reach the end of my time horizon, I can flip this around again. And now this is my reach avoid set. So this is a set of states for which if I start inside of that set, I'm guaranteed to reach my goal without entering the obstacle along the way. So this is great. This is really powerful stuff, and we use it a lot. It has some nice advantages. You have safety and goal satisfaction guarantees, because again, you're essentially doing dynamic programming here. And you are given the optimal control from this, because in the end, you have this value function with gradients that point in the direction of where you need to go. So it's essentially a generalized control Lyapunov function. There's a downside, which is that this is really slow and often totally intractable. So I'm gridding up my entire state space, and I'm solving this updated equation at every single point in space and at every single point in time. So when I have a 1D system, that in this particular example is 0.2 seconds, when I added a second dimension, I'm adding exponentially more grid points to reason over. So 0.5, then we get to 10, then very quickly it becomes completely intractable for higher dimensional systems.
So in your formulation, it seems that you don't need to stay in the goal during the time horizon. Like you just need to be in the goal at some time instant.
Yeah, that's a great insight. So there's and you pointed out what I was looking at was really more of a tube formulation where we asked, can you reach the goal at least once, briefly within this time horizon? There's another formulation that asks, I want to make sure that I get to this goal at exactly this time. And then you can also make it a little bit more complicated to say, I want to get to this goal at this time and then stay inside of the goal. So it depends on the problem setup that you're interested in. Similarly with the avoid sets, you can say, I want to avoid this obstacle for all of time, I want to avoid this obstacle at exactly this time, etc. Thank you. Okay, so this is very difficult to solve in real time or even at all for a lot of situations. And so what I'm going to talk about is trying to add efficiency to this. Now here's a few examples of what people have tried to do for robust but efficient control. On one end we have just pre-compute everything. So this is a quad rotor backflip case where you carefully pre-compute every single component of the quad rotor backflip and all the possible disturbances and then go ahead and implement it online after all the computation. Slightly more online are these particular cases where in both situations, this one's at Berkeley and this is, I believe, at Stanford, you need to find a nominal trajectory using the full dynamics of your system, which can be difficult if your dynamics are high dimensional, but it gives you a controller that stays robust with regards to disturbances like wind. So you know that you can stay within a particular tube around this nominal trajectory. And then trying to get even faster, this is a fun project from Ani Majumdar at Princeton, which is saying, okay, what if I have a bunch of motion primitives? So I have a toolbox of a bunch of little trajectories, and I pre-compute safety bounds around each of these ahead of time. Then online, all I do is stack these trajectories up together in such a way that I maintain safety as I go through it. And then finally, this is from Michigan, which is on computing a lower dimensional forward reachable set with an understanding of how points in the set map back to parameters on the high dimensional system. So these are all very nice, but a lot of them are fairly complicated in order to do the pre-computation to do online, and the online algorithm has to be modified quite a bit. So we were interested in trying to find something that was a little bit more modular, and we derived a lot of inspiration from cognitive science. So there's a fair amount of research in cognitive science that suggests that humans, when trying to do planning and prediction, use simplified models for those, where you plan using a simple model, and then you have some notion of the error bound that you would have around this model. So think of this for yourself when you're pouring a cup of coffee. Your hand is a very high dimensional system, every single joint in it. Planning it exactly would be very difficult. But instead you can plan using a very kind of cartoonish version of what you think you should do for pouring it, and you have some understanding of how that maps back to the high dimensional system that you are. So can we do something similar? Can we have our high dimensional system plan using something low dimensional, like that point in configuration space, with an understanding about how the safety constraints map back to the high dimensional system? So that's what we're going to be trying to show. Here is an example of where we want to get to. So here's a model of a plane that is tracking a lower dimensional plan and is going to stay within this particular bound as it does it. Okay, so I showed the very slow reachability analysis, and I showed the very fast, rapidly exploring random trees. What we want to do is something in between where we plan using our very, very simple system, but with a notion of how that will map back to our high dimensional system, so that when we execute it, we will stay within that bound. Note that planning with the bound around the low dimensional system is equivalent to augmenting my obstacles by that same bound, planning around these augmented obstacles, and then trying to track that. Where I may violate the augmented obstacles, but I will never violate it by more than this error bound. Okay, so here I'm mapping over those same things. Here's a low dimensional plan that I'd like to make and the higher dimensional tracking that I'd like to do. And I will call these the tracking agent and the planning agent respectively. And what I'm going to do is set up a game between these two systems. A pursuit evasion game where I, the high dimensional system, I'm trying to chase the lower dimensional system as it navigates through the space. And in the worst possible case, let's assume that that low dimensional system is being as difficult as possible to track. Now this is actually very similar to an old school game theory problem called, the Homicidal Chauffeur problem by Rufus Isaacs in 1951, where he said, okay, I'm going to assume that I have a homicidal chauffeur that is trying to run over a pedestrian. The homicidal chauffeur has this model, it's a Dubin's car, where it has a fixed speed that is higher than the pedestrian, but it has this rate of turning that it has to obey, and so it can't sharply turn. The pedestrian, however, is a bit more maneuverable because they directly control their x and y velocity, but they run at a slower velocity than the car. And you can imagine the types of applications he was interested in, given this particular example. He was asking, given this pursuit evasion game, where my pursuer in our case is the tracking agent and the evader in our case is the planning agent, what are the set of states such that I am guaranteed to run over this pedestrian? And so you can see that it's exactly a reachability game, where now the goal is wherever the pedestrian is currently. That is not what we're trying to solve. We instead are interested in saying, if I am trying to chase this planning agent, what is a bound that I'm guaranteed to stay within relative to that planning agent? So our question will be, what will be the maximum relative state over time? Or note here that maximum relative state over time is equivalent to saying worst possible tracking error bound, or tracking error over time, which is equivalent to saying the tracking error bound. So our goal here is to map the relative state between the tracking and the planning agent to the worst possible error that could occur over time. So to do that, we care about the relative states, and so we need to define the relative dynamics. So first, I will set my planning agent to the origin, and I will measure the dynamics of my tracking agent relative to the planning agent. Remember, our goal will always be around the planning agent, so I need to know where I am relative to them. In this particular case, it's very simple. You take your Dubin's car dynamics, the car dynamics, and you subtract out the appropriate dynamics of the lower dimensional planning system. In general, this could involve some rotations or whatnot to define this, but here we have it very simply. Okay, so we've defined our relative dynamics. Now I define a cost function, just like I did earlier, where now my cost function is simply distance to the origin, where again, remember, the origin is where the planning agent is. And so I want to measure the highest possible cost that occurs over time as I'm trying to track this agent as well as possible. So I want to capture the maximum cost of optimal trajectories over time, because this maximum cost will relate to the maximum relative state. So this, you should look very familiar to the map that I showed before. We're here now, instead we're doing a supremum over time of the cost of our trajectories. And now, again, we're not interested in just any trajectories. We're interested in the trajectories where, in the worst case, the planning system is trying to maximize this cost. It's actively trying to avoid you. And you, the tracking system, are trying to minimize this cost. You are trying to chase it and trying to get as close as possible to it. So we throw in that soup imp again. And we go ahead and run the system using Ian's level set method toolbox, and this is what we end up with. And this did not make any sense to me intuitively. So I broke it down, and let's talk about what is happening here. So here's my function that I'm going to propagate over time, and I'm taking 3 different slices of this function, and you see them here. So these slices are actually in 2D. This is x, y. There's a third dimension, which is theta, if you recall. So this is a slice when the car is moving to the right, so it's at theta of 0. Here's what the full 3-dimensional slices look like. Now you can think of each one of these as candidate tracking error bounds. So bounds that we are trying to see if they will be valid for our system. So let's start with some nice big bound. And remember, our planning agent is at the origin here. And our tracking agent is pointed to the right, and it has some radius of curvature that it needs to stay within. So if this is my candidate tracking error bound, what are the set of states I can start in such that I'm guaranteed to stay inside of this bound? Well, you can imagine if I start right here on the edge, pointing to the right, I will have to leave in order to come back in, right? So that's not an okay state. In fact, the state that would work is one where I can, just barely stay within the bound. So we would expect this to pull back from the right for the set of states that you can start in. If I start down here, well, this is fine as long as my radius of curvature is tighter than that of the error bound, right? And if I start back here, well, this is fine because I'm just entering right into the error bound set. So for a large tracking error bound, you would imagine this to look something like this. So if I start inside of this set, I could stay inside of that. Now, as this set gets tighter and tighter, you can imagine you eventually get to a point where your radius is not tight enough to stay within this bound if you're on the edge. And even if you're right here, maybe you have to exit to come back in. Like it's too tight to be able to stay within. And as this goes down and vanishes, you can't stay exactly on top of the planar at all times. So now that we have that perspective, let's run this again and think about that and if this matches our intuition for what happens for the error bound. So you see the value function propagating, you see it pulling away from the side as we expected, and eventually you get to a point where in this case a radius of 0.5 is not valid. But we keep running this, eventually it converges, and we see that in this particular case these two slices are totally valid. If I start inside of this purple set, I'm guaranteed to stay inside of this blue one. If I start inside of this red one, I'm guaranteed to stay inside of this blue one. So we still have many possible error bounds that we could stay within. Now, in general, we're interested in reducing error as much as possible. And so now that I have my converged value function, I'm going to choose the slice that is the most minimum that I can get, plus a little bit of delta, so that I get the tightest error bound possible. And this will give me my smallest invariant level set. So this is what it looks like in 3D. So you can imagine if I rotate and stack this, because again the third dimension is theta, that's what it looks like. And this is my tracking error bound. This is the set of states that if I start inside of this set, I'm guaranteed to stay within that bound. However, corkscrews are kind of weird to plan with, and in fact my planning system is not aware of theta at all. It only is aware of x and y. If you remember, it's just directly controls velocity in x and y. And so I need to project this down onto the xy dimensions, and this will be the tracking error bound that I use for planning. And you can see that what the actual optimal thing to do is your planning agent's in the center, and you, the tracking agent, are essentially doing donuts around it. So it tries to run away, and you're turning as tight as possible, and it keeps running away, and you're essentially circling it like a shark or something. So that's the tightest possible bound that you can stay within relative to the planning system. Okay, so that was a lot. The output here is our tracking error bound and also a tracking controller. Because again, I'm given a value function that has gradients that point in the direction that I need to go. So I can use this as a control Lyapunov function. Now, we took a tracking system model and our planning system model. We found the relative dynamics. They gave us the tracking controller and tracking error bound that we'll use for online control and the online planning algorithm. Now I'm going to show the online planning algorithm, our first simulation, and then we can stop for any questions. Okay. So here's some environment that we don't know about a priori. Let's assume for now that the obstacles are static. And I pre-computed my tracking error bound and my tracking controller. Now for my online algorithm, I first start off by just figuring out where I am. Let's assume that we start here. And based on where I am, I choose to initialize my planning so that we are within a tracking error bound of each other. So in this case, I'm going to start it right here. I then plug this into my path or trajectory planner. Whatever you want to use, RRT, model predictive control, ILQR, whatever, we don't know. And I also plug in the environment, the locally sensed obstacles. And I augment these obstacles by the tracking error bound. So this path or trajectory planner has its state, it has the obstacles, and it outputs wherever it wants to go next, however it does that. And then we measure the relative state between us and this next planning state. Based on this relative state, where I assume that this is 0 and look at the relative state of me compared to that, all I need to do is plug that into my pre-computed value function to tell me what is the best control to chase this state. And so I apply that tracking control. I may not be able to track it exactly, but I know that I'll stay within one error bound of that planning system. I then continue and just do this on a loop. I augment obstacles, I plan, and then I just plug this into the pre-computed relative dynamics controller, and I try to chase it. And so all we're really doing is allowing you to continue to use whatever path or trajectory planner that you want to use that's very quick and online, and doing 2 extra steps. One is augmenting obstacles, which we typically do anyway in robotics. And the second is looking up the best control to try to chase this plan. So this was our first simulation for this. Here is a 10-dimensional near-hover quadcopter model. And we wanted to get to this point over here across the room. And there are some obstacles that we haven't sensed yet. If I were to try to do the full reachability analysis on this 10-dimensional system, first I would need to know where the obstacles are. But even if I did know where the obstacles are, it would take like the time that the universe has existed or something to compute this. So it's just not feasible at all. So instead, we do this pre-computation where I would like to be able to plan using this very simple 3D model. So I compute my relative dynamics for this, run this through my pre-computation, and I end up with this complicated 10-dimensional relative dynamics tracking error bound. I project this down onto X, Y, and Z, and in this particular case, it looks like a box in X, Y, and Z. So now, I'm planning using RRT, that's what this little green dot is doing. As it senses obstacles, the obstacles turn red and it replans. And in blue, you see the 10-dimensional system trying to chase it. And even when the system makes a sharp turn, like you'll see it's about to make a sharp turn when it senses this obstacle, because we accounted for worst case situations for the planning, we are able to stay within this bound. So by assuming that the planning system is adversarial, that means even when it does something that seems kind of wild, like doing a 180-degree turn, we are able to stay within this bound. So this allows us to completely decouple the planning from the tracking and safety. Before I continue, are there any questions on that?
I'm wondering, how do we know, so what's the property of the tracking model to ensure bounded tracking error?
Oh, that's a great question. I love that question. And it's a really great point. So I basically assumed in all of this that I would always be able to stay within a particular bound that is static around the planner. But you can imagine if this planning algorithm was very, very fast, it could be getting further and further away from me over time, and I wouldn't be able to catch up to it. And so in that particular case, you would have a time-varying error bound that would grow over time, which is okay because we have implemented that theory, it works, and also since we are assuming worst-case assumptions, often in practice we don't have worst-case assumptions. The planner's not trying to actively escape you, it's trying to get to the goal, so you can kind of reset as you get closer. In practice, though, since you are designing the planning algorithm, it's totally imaginary, you are coming up with what model you want to use, you can adaptively choose it such that you have a higher control authority than it, and you're able to stay within this bound. But the mathematical properties of, given a random set of dynamics, what are the constraints on the control system that you must have such that this converges, is something that is not explored yet. And if you're interested, I would love to talk to you about it. Was there another question?
Just a quick question. Is this a real-time replay?
Oh yeah, that's a great question. Yeah, this is happening in real time. And we'll see a few examples in hardware as well.
So when you project the 3D bound onto like a plane, I feel like you're losing some information. So do you think there's a better way to complete that?
Yeah, that's a great question. So we are still using the full, in this case, the 3-dimensional or 10-dimensional information for the controller, because that's still defined in the full relative state space. So you still need to have that 10-dimensional value function in order to figure out what control to use to stay inside of that. For the planning system, because in this case, the planning system is only aware of 3 dimensions, you can't give it more information than what the bound is in X, Y, and Z. I think it's a really interesting question to ask, what if you augmented the planning system to allow it to account for other dimensions as it's planning? And in fact, one of the next projects I'll be talking about is starting to address that. Any other questions about this? Okay, great. All right, so that was the safety and the efficiency, and now I'd like to talk about some other projects that we've done using this framework. So one of the main issues with this is that it's fairly conservative, because I'm assuming this adversarial assumption that the planning algorithm is always trying to escape me, when in reality, it's not trying to escape me, it's trying to get to the goal. But in order to completely decouple the safety from the planning, this was necessary. So in reality, there might be a control such that this airplane could get in between these obstacles. But because I'm assuming that the planning system could make a 180 turn in the middle of it, it's no longer a safe thing to do. So how can we deal with this conservativeness issue? Well, at the time that I was doing this, I was reading this book, Thinking Fast and Slow, by Daniel Kahneman. He's a Nobel Prize winner in economics and behavioral psychology. And he asserted that humans think in two modes. We have our system one, which is our fast, intuitive way of thinking, which is continuously scans the environment, it's fast but error-prone, and it works automatically and effortlessly via shortcuts, impulses, and intuition. So this is kind of our default mode. But we are able to switch into a more slow and deliberate and conscious mode when we're doing something like making that tricky left-hand turn or doing long division. And this mode is used for specific problems only if necessary. It takes effort, and it's slow but reliable. And my lab is the hybrid systems lab, and so I was very excited by this, being like, whoa, humans are like hybrid systems. Can we try to incorporate this into our planning? So here I'm showing again my tracking system model. I'm saying, what if instead of just using one planning mode, I had two possible modes? In the very simplest case, let's just assume that they're the exact same dynamics, but one is slower than the other. So the control bounds on one is slower than the other one. So what this would be like is a planner that moves very slowly through the space. So this would be like the tracking system trying to chase me. I am very slow, and so the resulting error bound will be very small because it's easy to keep up with me, but I'll also move slowly through the space. On the other hand, this one would be like chasing Usain Bolt as he's like running super fast, which is hard, and so the error bound will be much bigger, but you'll be able to traverse the space more quickly. So now this means that I have choices in which bound I want to use. So there's the fast mode with the higher, bigger error bound, and then there's the slow mode with the tighter bound. So when I sample points that I want to take, I check if they're in collision. If one is in collision with the larger error bound, I ask, well, if I had switched into my slower, more careful bound, would I be able to get through this obstacle? So this allows us to very quickly traverse the space when there's what is sparse and there's few obstacles, but then switch into a slower and more careful and less error-prone method of planning when it's more densely cluttered. Any questions on this? Oh, let me also say, switching safely is non-trivial. We also have to do a little bit of reachability to make sure that when you switch between modes, you do it in a safe way. But given that, we have a proof of guaranteed safety throughout this process. So here's a particular example that we did in hardware. There's a quadcopter that you'll see once I start playing, running around. I bought these little lanterns off of Amazon, and it detects the objects. This is in a motion capture room, so it detects the objects, and it tries to navigate around them. It starts by default, and it's a larger error bound, and then it switches into the smaller one in order to navigate between the obstacles. You see, it switches in here. And so this was for ICRA 1 year. Okay, any questions on this meta planning?
So how did you define the width of the boundaries around the obstacles? Did you optimize to achieve the balance between safety and...
Oh, that's a great question. Like, did we adaptively choose how fast it was going so that we knew how big the bound would be so that we could choose the different ones? No, we didn't. We just chose two different speeds in this particular case. When I talk about the future work, we're interested in looking at slightly more nuanced situations like planning with a really low dimensional system versus planning with a higher dimensional system that's more accurate. And we're also interested in looking in kind of adaptively choosing the bound that you need based on the certain environment. So great question. If I don't answer it at the end of the talk, please ask me again. Okay. Great, so that was one project that we did using this framework. Another project, just since I don't have a lot of time, is using sum of squares optimization instead of the level set toolbox to solve this. So using sum of squares optimization, we can deal with higher dimensional and more coupled systems, but we end up with a slightly more conservative solution. So this was an 8D highly coupled plane model tracking, I think, a 5-dimensional plane model throughout an environment. And this was a collaboration with Marco Pavone's lab at Stanford. I started working with trying to deal with obstacles that aren't static, and in particular, the most annoying moving obstacles, humans. And so we started a collaboration with Anka Dragan's lab in human-robot interaction at Berkeley, where we are predicting, in this case this is me, you see these predictions that are coming off of me, and the fast track algorithm is planning around these predictions in real time. We also then turn this into a multi-human, multi-robot scenario. So you see here me and my colleague Jaime are trying to navigate around each other. And then beyond what I've done, there's also some extensions that have happened. One in my lab for making this recursively feasible and recursively safe. So ensuring that you will always be able to get to your goal safely, and you won't end up stuck in an alleyway or something where you can't turn around easily. And then there's also a lab at Berkeley that does augmented reality, and so they're working on this setup where you can tell a bunch of quadcopters, I want you to go there and you there, and then you can go ahead and send a bunch of quadcopters to navigate through hoops in this case, and they're using our fast track algorithm in order to safely navigate through those hoops. Okay, so that's the technical part of the talk, and now I'm going to talk about future work, unless there's any more questions on the base work. Okay, great. So future work on this particular set of projects is continuous meta-planning. So this is related to your question, which is the response to a lot of psychologists to this thinking fast and slow work has been that no, humans don't have two discrete modes that they switch between. Rather, we have what's called a boundedly rational method of thinking, where we would be optimal, but we have a certain amount of compute that we can spend. And for a particular task, humans determine the value of computation for that particular task that associates with how much effort you will actually put into this. So rather than having two discrete modes, it's more of a continuum where you adaptively choose how much effort you're going to cognitively spend on a particular task. So there's a similar question of, can we have now a continuum of these error bounds where, given a particular environment, we say, I would really like to I would sacrifice moving this fast in order to be able to navigate through this particular environment. So you choose the error bound that you want. Similarly, meta-planning across planner fidelity. So before I was talking about using the exact same planning algorithm and model and just changing the physical speed at which they move. Again, me versus Usain Bolt. But instead, I think it's interesting to ask, what if you choose something that's very, very computationally efficient, like this 3D RRT, and you choose when you would rather switch into something that was a little bit more effort, like let's say MPC, and but it is higher fidelity, and so there's less of a model mismatch. So you'll be able to have a tighter bound there. And can you choose the speed at which you're willing to compute this? Next, safe learning for the tracking model and environmental uncertainty. I sit with a bunch of machine learning people at Berkeley, and every time I present on something like this, I always get the question, well, these safety guarantees are great, but they're for this particular model. I am assuming that that 10-dimensional tracking model is actually accurate and represents the full dimensional system. And it might not be true. It might be that you actually have some uncertainty in your own dynamics or in the environment or in the disturbance, the wind that is blowing on you. So is there a way that you don't have your whole pre-computation totally invalidated when you find out that this is wrong, but instead you can warm start your computation with a guess, like your previously computed safety analysis that was wrong, and update it in such a way that you are achieving exact or conservative guarantees on the resulting value function. So this is a little more on the theory side with something called warm start reachability, but we're hoping to apply it to real practical cases where you find out, oh, my mass was different, or oh, this environmental parameter is different. You learn about that, and then you reprocess your information efficiently rather than having to restart the whole computation all over again. And then finally, some more collaborations. So Ron Sudovan at Michigan is interested in incorporating this into his reachability trajectory design work. Borelli at Berkeley does the NPC lab and wants to add this into their tube MPC work. And then Sanjit Sesha is interested in incorporating this with their formal methods work at Berkeley as well. So that's all exciting. Longer term, you'll notice a pattern here in a lot of these projects. So we took inspiration from the fact that humans plan using simple models to come up with the fast track algorithm. We took inspiration from thinking fast and slow to extend that into the meta planning, where you switch between fast and slow modes. We're now going to update that by saying, no, actually, maybe it's more of this bounded rational method of thinking, and turn that into the continuous meta planning. And then similarly for the human prediction work, which I wasn't able to talk about today, we use very simple methods of predicting humans and reasoning over how confused we are about the humans right now. And so in general, I think that cognitive science is really interesting in that it studies frameworks of how humans think. And this is useful because humans need to operate in real time in the real world. And so can we learn from humans how our autonomous systems should function and steal frameworks from cognitive science and put that into our systems? Similarly, by understanding the frameworks of human cognition, can we find where humans fail and autonomous systems do well and are able to augment human performances by having this feedback? And that is all my work. Here are the different GitHub code repositories for all this work if you're interested in it. And I'd be happy to talk more offline or in questions now. Thank you.
Any questions?
I know I answered a lot during it, so.
That's good.
How would you see the role of sampling-based verification methods that would maybe provide a different way than what you presented of adjusting the precision versus efficiency?
Yeah, I think that that's a great direction to be moving in. So all of this was primarily grid-based and doing deterministic things. And we actually just got a new postdoc from Stanford who loves POMVPs and Julia and sampling-based methods. And so we're going to try to incorporate or redo a lot of these projects using sampling-based methods for scalability. I think that you're absolutely on point that thinking about adjusting the sampling rate as a method of switching kind of adaptively between fast and slow is a really cool direction. But I have not done that yet. So great idea.
I have a question. So your whole premise was that the cost for these various graphic models like cones kind of stops at a cost equals zero. And so you remain safe and the method remains robust. But instead of the Usain Bolt model, could you have like the James Bond model where you actually accept a certain amount of loss, so a positive cost, in your equation in order to be able to maybe unscathed or maybe only slightly singed get through a series of obstacles. So it's a way of perhaps handling the situations that we all end up with now and then. They're going to falling.
Yeah.
Or that's kind of a benign case unless you're 80 years old and osteoporotic. But or in case of a crash, can you use this to figure out what's the minimum damage that a particular scenario will inflict on you, given your fast planning kind of like oh crap moment? I'm just wondering about sensibility.
That's a great idea. I mean, you're absolutely right. When you're in a crowded environment, you may end up bumping up against someone and thinking about redefining what safety means, rather than safety being like you are never allowed to come in physical contact with anything ever. Asking instead, what is the maximum force I'm willing to exert on another object and still be fine, and finding the appropriate level set for that. It's really, I've never thought of that before. That's a great idea. I like that. Any other questions?
maybe you have said this, I'm not sure, but if you actually are able to plan faster ahead, yeah, if I imagine I would be on a racetrack, then I would basically know, okay, I have to follow this particular way along. But I could already see that I'm basically making a lot of turns, and maybe that's not very efficient. So I could basically feed back into my planning algorithm some abstract model of my dynamics, because maybe that would allow you to kind of feed back into the planning algorithm.
That's a really interesting idea. I think that reminds me kind of like anytime planning algorithms, where you start off with a very, very coarse plan, and then if you have time, if you still haven't reached that point, you refine it more and more and more based on how much time you currently have. I have not done that, but I think that would be a really cool project to see. I think that there's some work in that in different areas, but in terms of ensuring safety while you're doing that, I think that's still an open question. So, very cool. Oh, okay.
All right, and I was just wondering, in the case of the non-static objects, what were like the sort of constraints on how you're allowed to move for it to plan properly? Like you could dash to it if it was flying around. Like do you have any constraints on like how fast you assume you were moving or stuff like that?
Absolutely. So I guess since we have a little bit of time, I can talk a little bit about that particular project. So when avoiding humans, what you would ideally like to do is avoid their forward reachable set for the time horizon. That means if my human is right here, and my time horizon is 10 seconds, I would like to avoid every single possible state that a human could get to in 10 seconds, and use that as your obstacle for right now. Now, this is nice for worst case analysis and safety critical scenarios. But as we talked about, when you have a lot of humans around, safety critical isn't always very helpful, because you end up in a freezing the robot situation where there's nowhere you can go because everything is unsafe. And so instead, we assume that humans have some intent, so they have some goals in the state space that they're interested in. Let's say, like, there's a door here and like a laptop here or something. And you reason over what is the probability that the human will take a particular action given these goals that I know in the space. And using this, I come up with a Bayesian distribution over where I believe the human might go next. And this will be a subset of the forward reachable set. And this works great as long as humans are perfectly rational and do exactly what they're supposed to and go to their goals. The problem is that humans aren't always perfectly rational. So our classic example is a bee flies in through the door, and the robot might not be able to sense bees. Even if it senses bees, it might not understand what bees are and humans' relationship to bees. And so when the human freaks out, it has no idea what's happening or why. And so rather than trying to come up with the perfect model of a human so we could perfectly predict this, we instead reason over how confused we are right now in what the human is doing. So we do a Bayesian update over the term that controls the variance of this distribution. So when the human aligns with the action that we expect, we have this tight distribution. When the human does something very confusing and unexpected, like going towards some unmodeled goal or something, we increase the variance of our distribution, and in the limit, it ends up being the reachable set, the forward reachable set. And so this is nice because when humans are exhibiting some structure that you can predict, you're able to tighten this distribution and navigate through the space. But when you get more and more confused about the human taking different directions or acting erratically, then you give them more and more space and navigate more cautiously around them. So that was a whole other set of projects that I didn't have time to get into today. But your question was, how do you, as the robot, deal with navigating safely around this? For us, we would sample a point in the state space, look at the error bound around that point, and then if we sample a point that overlaps with the distribution, we integrate the probability mass within that error bound, and if it's greater than our threshold, we reject that point in our trajectory. So we don't have guarantees anymore because humans, but we have probability safety assurances, we call it. And in practice, we're able to fairly well navigate around each other without too many terrible accidents, collisions. Okay. Oh, sorry, there's one more.
One last question, yeah.
What are ways in which people are using neural networks? So what I've seen is using them as policies in NPC or something like that, or training Lyapunov functions which are actually neural networks with specific forms. It seems that because of the overhead for training them, it would more be suitable for the pre-computation part in whatever that method is. Maybe you have a unique perspective from that trade-off.
Yeah, that's a great question. So I think you absolutely hit it on the nose in that neural networks are very, very powerful when they have enough data. And it's tricky in robotics, as you know, because trajectories take a very long time to gather enough for that to be able to create a policy or a value function from scratch just based on this. So one thing that I'm excited about is with this safe learning project, where you start with the pre-computation based on models that may be totally incorrect, and you seed your learning with this value function that you've computed, and you update it based on the trajectories that you get in real time. So I hope that that will help bootstrap your policy as you're learning by starting with what you know about models. Okay, thank you so much. I really appreciate you taking the time.